All right, so now it's time for we have the last talk for the day, but before that, we will also share a very wonderful video that one of our attendees in the past and trainers have sent out with us. Let me play this for you all.
Hello everyone, I'm very happy to attend the hardwear.io conference live this year, where we can find a lot of good trainings, talks and also audience. Actually, it's a little bit sad that we cannot share drinks with each other, but still we can do it virtually. So cheers guys, and see you maybe later. Bye bye.
So thank you, Sebastian, for that video. Since he mentioned that we can't have drinks together, and one of the things that I have missed in a lot of online conferences that I have attended in the past few months is we are not able to interact and make new friends and network around socially, right? That's one of the reasons why we all go to conference, including me. So at hardwear.io, we created this initiative called Fix Up, where you could grow your hardware hacker network by signing up and letting us know what are your interests, what would you like to learn, share, and interact with other friendly hackers. Hence, we would, based on your input, we would find you a match from the other attendees who filled up the form and connect you both for a one-to-one 30 minutes video call. This way you could find a job, you could find a co-researcher or a mentor, or you could also probably find a client, right? So please do sign up for hardwear.io Fix Up. We've got some really good hackers onboarded, and they are waiting to meet you all. Saying this, moving to the last talk for the day. It's by Grant and Marius, reverse engineering and emulating Samsung Shannon Baseband. Grant is a researcher specializing in mobile and firmware vulnerabilities. He recently joined the Qualcomm product security team. Marius is a PhD researcher at FU Amsterdam, and he's also the lead author for and maintainer of Avatar 2 framework. So over to you, Marius and Grant, to begin your presentation.
Thanks for the introduction. We will get the slides up immediately, and yeah, here we go, I think.
All right, well, thanks again for the introduction. We're really excited to be presenting our work on doing a lot of Shannon and emulation. And I'm Grant, and my co-author Marius. We worked really hard on this. And along with us, we have a huge team behind us who made this possible across 2 different research groups and a 6-hour time zone. So we made it work. A little bit about me. I recently graduated from the University of Florida with my PhD. And from there, I went directly to Qualcomm to work on the product security team, also known as QPSI. There in my PhD, I worked on Android security and firmware analysis. And on QPSI, I'm now working on modem security.
And I'm Marius. Hi, I'm, as mentioned before, a postdoc at Vrije Universiteit Amsterdam within the Fuzzing group, and I'm focusing on building better tooling for dynamic analysis of embedded devices of all sorts. And one of those devices is the Shannon Baseband, which we will dissect in this talk.
Yeah, so a little bit of an outline of what we're going to be covering today. We're going to start with an intro to cellular and basebands in general, and then talk about the motivation why we decided to look at Shannon, along with the tools we use to actually investigate Shannon in a scalable way. We'll talk about an overview of the firmware platform, how we dug into the firmware and where we got it. Then we'll go over, we'll start with an overview of ShannonOS, and how we use a mod kit to change the behavior of the baseband in our emulator, and how we were able to use that to do fuzzing with AFL, and finally we'll conclude. So to make sure we're on the same page, cellular networks use these things called cellular protocols, and your phones also use them to communicate across a wireless medium. These protocols have been around and have gone through many different generations over the last 30 years. They're designed by a committee, and it's up to the individual manufacturers to implement them how they'd like. And these protocols cover everything from the physical layer and up. So effectively, they might use TCP/IP at the very highest layers, but everything below that is cellular specific. Now, basebands implement the other half of the cellular protocols to communicate over the air. And if you're using a smartphone today and you're not using like a brick, you'll have a baseband processor in your device, which means it is a separate processor from the normal application processor running in the background. Individual manufacturers will implement their own version of the cellular protocols, and Shannon happens to be a particular implementation from Samsung.
And you may ask at this point, why would you make the hassle and why would we look at those basebands, the Shannon baseband? What's the motivation behind it? So basically, we have two different motivations. On the one hand, phones, or recently there are more and more efforts of having free and open source phones with open software running on them. But basebands are these large, undocumented, closed source component running on most phones. So even if you have an open source firmware running on your application processor, there's still the baseband, which is mostly code which you don't control, you don't know about. So if we will reverse it and get more insight, we may build building blocks to eventually implement an open source version of a baseband firmware. Furthermore, as we don't know too much, as there's no source code available, it's not really publicly documented, we can also don't make any assertions about the security of the baseband processor and the firmware. So understanding it is really crucial to understand the security and eventually maybe find bugs and fix it. So we're starting, we realized that just manually static reverse engineering is not really an option here. The baseband firmware we are looking at, the Shannon one, is around a 40 megabyte binary blob in size. And we determined that there are at least 4 million lines of source code involved to make this firmware happen. So both of us are pretty big fans of dynamic analysis, and we thought it would certainly speed up our reverse engineering efforts. But for doing on-device debugging and on-device dynamic analysis, we would need to exploit the phone and the baseband processor itself, because debugging features are disabled on all consumer devices. And we decided, okay, that's really big of a hassle to find a bug, exploit it, and so on. And I mean, ideally, to find a bug, we will need to have it reverse engineered first. So we decided, let's build an emulator instead, where we have full control and see how far we got. Of course, this has its own problems and challenges, which we will talk about in this talk, and mostly that there's a lot of custom and undocumented hardware we have to deal with. With that in mind, I just want to give you a brief overview about the different tools we used in this process, because they really helped us to understand the baseband. So firstly, we use Ghidra as static reverse engineering framework. The main reason for us to use it is that it has reasonable collaboration features, which are working for us as we were located in different time zones. The second tool we were using is Panda, which is a dynamic reverse engineering framework based on QEMU. QEMU itself is a popular full system emulator. And what Panda allows us, besides full system emulation itself, it allows us to register callbacks to be called during emulation. So we can really introspect the emulation process itself. And additionally, it had recently released some Python wrappers, which make our life very easy in controlling. But then Panda itself is still based more for desktop systems and ordinary kind of software and operating systems. So we brought Avatar 2 in the loop, which is a Python framework which has wrappers around different emulators. It's meant for orchestrating them and orchestrating embedded devices to aid dynamic analysis. And two of the main perks we were using here is the so-called configurable machine, which allows us to quickly support different targets, such as the baseband, and it allows to create peripheral models in Python. So for hardware and peripherals we don't know, we can create Python code, which will then interact directly with the Panda emulator. More to that later. For now, as you have the brief overview of the tooling, let's start to look at the actual hardware of the Shannon baseband.
Yeah, so The Shannon Baseband only lives on Samsung Exynos platform, which is a in-house SoC from Samsung. Phones sold in the United States actually use Qualcomm's SoC, and therefore they end up using Qualcomm's modem. So for doing any kind of research on Shannon, you'll need to buy essentially a global edition Samsung device, which for me, because I'm based in the United States, it was a little bit harder. I had to buy from a third-party website. But if you have this, you can then use the Shannon baseband. And really, Shannon lives somewhere on this floor plan of this this decapped SoC. But we don't know where it lives, but it could be there, it could be somewhere else. But it's effectively part of this. At least the digital part is within the basebands, their overall SoC. And for our work, we focus on the Samsung S10 and S7. This was because we bought an S10 and we had an S7 on site. So we had something we could compare against when developing our emulator. And after doing a lot of research, we ended up kind of compiling together a block diagram of what we understood Shannon's relationship to the application processor, or the AP. ShannonOS and Shannon Baseband runs in the cellular processor and communicates with the application processor via shared memory. And the Shannon processor will have connection to hardware peripherals that the normal, application processor running Android won't. So for the purposes of this talk, we'll be really focusing on emulating this portion of the block diagram. We look a little bit into the application processor's interaction with the baseband to help get us some insight into how to boot the baseband. But for the most part, our emulator will only emulate this this box on the left, and we won't really be like a full system emulation, including Android.
And the first task when starting both reversing the emulation target or an unknown target is to figure out the CPU architecture we're dealing with. And we knew from previous work that it's likely to be in Cortex-R7, and later on during our efforts also realized that for the S10, it's actually a Cortex-R8 MCU running those baseband firmware. And unfortunately, Panda does not support these ARM variants, these ARM profiles out of the box. So it could be a showstopper. We looked a little bit more into code of Panda and realized, okay, it supports the R5 profile of Cortex-R5. And we wondered what would be required to get the R7 and R8 profile working on it. And it turns out actually not too much. It's really just a couple of lines of changes which are needed, because we can use the Cortex-R5 initialization function and basically just change a single entry and are able to start emulation of the Cortex-R7 processor in this case. The entry we changed here in the middle of the slide is the PM7D region, and we set it to 32. So this value is basically to specify the number of MPU table entries. The Shannon baseband or the Cortex-R processor uses a memory protection unit, which just protects certain regions of memory and is not a full-blown memory management unit as we have on desktop computers. And we also know of the existence of the MPU from a previous talk, which was at Recon 2016, and it was already well reversed. However, in the talk back then, which was also showing the presence of the MPU and the MPU tables, the firmware itself was engineered by extracting it from a RAM dump of a running device. And we were thinking, if we will just have a RAM dump, which may be difficult to get in the first place, we miss a lot of state and a lot of parts in the emulation and toolchain which would go on during boot. So we looked into how to actually get the firmware from scratch.
And getting the firmware actually wasn't that difficult. The firmware is present in all of the factory images from Samsung phones. The hardest part is probably the time it takes to download, because Samsung won't host the firmware themselves. They'll, parents' third-party websites will host it and then sell it to you, which is a little weird. But if you are waiting to do the free version and wait for your download and get your firmware, it's a zip file. You can then unzip it into different partitions. In our case, we're only interested in the cellular processor partition, which is the tar file. You can untar, and then you'll be left with two files, modem.bin and modemdebug.bin. Now, we'd heard, as a rumor, that the modem.bin was encrypted. Looking into it, though, there didn't seem to be anything of the sort. So apparently in the past it had been encrypted, but for us in the phones we looked at, it wasn't. So this was great. We didn't have any kind of barriers to stop us. Alternatively, if you didn't want to do this download and you have a Samsung phone that you know is a Shannon model, meaning it ends in F in terms of the device code, and if you have root, you can just extract the firmware directly from the radio partition. So to look more into the modem.bin file, it's fairly straightforward. It has a simple header that is known as the table of contents header, which is broken up into a couple sections, the entry name, the file offset into this modem.bin file, the load address, the size, the CRC, and the count or entry ID. This is repeated throughout the rest of the header into multiple different sections, which are defined. So for our purposes, we're only interested in the boot and main sections, because these are the only two sections which are really related to the baseband. And further looking into it, we're really going to start with the boot section, because that is what that's the first code that the baseband would execute when starting out. And from an emulation perspective, we need to go there. So following the initial offset that's given, we can then use this to start looking at the initial bytes that are there. And we can, if you've done any ARM reverse engineering, you'll notice there's a particular pattern of bytes, essentially these E's here, which actually correspond to ARM32 always conditionals, which is a good indicator that there's a lot of essentially jumps here, or instructions that are always being run. And disassembling this initial byte sequence in Ghidra is actually confirmed this. It actually showed that, hey, look, these are actually the interrupt vector tables. So they're the exception vectors. We can jump straight to them and start disassembling and emulating from this point forward. And before we got significantly further into actually doing the emulation, we need to take a step back, because well, we noticed that there's this region in the actual modem.bin that has a whole lot of debugging information. And so we want to leverage that and kind of liberate that to something we can like visualize and see in a stream as you're emulating, because there's over 150,000 debug messages. So we wrote a Ghidra Python script to actually auto-type these regions, which have they helpfully have a magic value, so you don't need to do any kind of cross-reference finding. All we really did is found that initial those offsets, and then we would apply a type to them, and then apply a nice label. And you can see this is what it looks like after having applied the type on the right here. But funnily, you should notice that a significant portion of the baseband is just debugging strings. That whole green region is debugging strings.
And that's also very nice for us for our emulation, because we can annotate different parts of the firmware. And let's take a step back and look at the overview. Now we have basically everything we would need to actually start emulating and not just talking about it. We know the CPU architecture. We got the memory map from the MPU tables and the table of contents file. We know the entry points, which are the boot vectors, and as bonus, we have the debugging strings. So we wrote a small avatar2 script to kick all of it off, shown below here. That's missing some parts, but the main important parts are there. We initialize an avatar object with specifying the Cortex R7 profile. We add a Panda target with the according entry address, and then just load the modem file at the different locations in the emulator and start the emulation. So being there, we got pretty much through the boot code, but we realized, hey, we don't have any output so far, which is not surprising at all, because our output is coming via a UART peripheral. And of course, we don't emulate it if we just have a raw full system emulation without any more knowledge about peripherals. So we started writing those sorts of avatar peripherals. In this case, UART peripheral. And we see it here on the right on the slide. So it's basically really just a Python class where we define read and write handler, which do different actions at different offsets. And here, for instance, if to this peripheral is written from the firmware, we will just give output on the command line. And this corresponds to the firmware, to the boot code on the left in this case. So we will see now with this peripheral during emulation that we get the sharp symbol. and the contents of R0 later on. So we get through the boot code, we even get the first initial output stating a little bit about the version, but then we really fast hit a major roadblock. There was this huge function called pal init1, which we just couldn't get past with emulation. So from looking at the source code, not the source code, the binary code, the disassembled code, and decompiled code, we realized it's really a huge monolithic function which is responsible of the initialization of the modem. So it activates the heap, it loads all kind of non-volatile storage items, it starts the different timers, initializes the digital signal processor and other peripherals, and it starts all the operating system, the real-time operating system tasks. So really being able to emulate and get passed through this function would be crucial for setting up the baseband state. Because if we would just skip this function and emulate later on, we basically miss all the sort of different state we would need to faithfully emulate what's going on. To give you a feeling of how this function looks like, I don't expect you to read everything of this or just take it in, soak it in, have a small look. All of these are different functions call, and each function is very likely to initialize their own subsystem on the modem. And there are lots of peripherals and unknown hardware involved. So how did we get passed through this function? Basically, the key point here was to give emulation wrappers or provide peripheral models for all the different peripherals which are touched. So we started with a very naive approach by just emulating peripherals one by one and figuring out for crashes or looking out for crashes of the baseband or seeing when we are looping infinitely and where do we loop infinitely. So we could then go on, look at the instruction counter of the emulator and then correspond to it in Ghidra to see, okay, where are we, what value would be expected from here. But this was very tedious. So we optimized a little bit more and started to directly log all sorts of MMIO accesses to see which peripherals need more modeling and when are we gone. Also here, we got quite far with this approach and could manually model some of the peripherals, but in the end, the real small idea which got us through it, which was inspired by another academic work, is to use a cyclic bit pattern. So this is basically whenever you would access the peripheral, it will just reply with another bit set in this specific memory location. The idea here is that during baseband initialization, the firmware often just writes some initialization code or like some initialization instructions to the peripheral, and then checks on memory cells if the peripheral says, hey, I'm ready to go. And it does so by just setting a bit to true. So this really helped us to get through a lot of initialization code very fast. Still, to really initialize and get through pal init1, we needed to partially emulate some more peripherals in detail, for instance, the digital signal processor, the shared memory interface, timers, and so on. And having all of this done, we finally reached the banner in the emulation. We could see output from our baseband. So we see here it was based on the development platform of a Cortex R7, but this doesn't mean that the baseband itself runs on a Cortex R7 core. The ACPM task later on annotates that it runs on a Cortex R8, as shown very down in the screen here. So now that we have the baseband booted and all the tasks running and so on, it's time to look at the Shannon operating system. Basically, the operating system has, as said before, a lot of different tasks, and the metadata are stored in task structs, shown here to the right. There are around 100 different tasks in the baseband, and the entries or the information stored in the task struct is things like the name pointer, what is the main function, what is the initialization function, and what's the stack base. So each task here has its own stack, and the stack base, to not be overflown by another task, is guarded by the magic constant ox.beef. Task itself communicates with each other over queues, and we discovered that there are more than 290 different queues in the baseband. So there can a lot of inter and intra-task communication happen. To give you also a small idea about the different tasks, this is a table of the tasks we extracted, and they're basically very nice split up into different subsystems based on the cellular standard. We have, for instance, the CC, the call control task, or the mobility management, which are sub features of the GSM standard. Next up in the operating system is scheduling and interrupts.
I made it back.
Ah, you're back. Okay, great.
Yeah, sorry about that. Your screen is black though.
Yeah, my screen went blank. Okay, so more technical problems.
Yeah, my internet just decided to completely
Yeah,
shut off.
so it didn't really manage. Okay, I will restart sharing. Sorry for that. Here we go.
Okay. All right. So yeah, so with all those tasks that we have, there's some scheduling that needs to go on to make sure that certain deadlines are met and certain interrupts are distributed to the right places. For the most part, the scheduler is fairly straightforward. Tasks will block, aka yield, when they receive an IPC message. And they can also be preempted by higher priority tasks or interrupts if they haven't been disabled. So the general flow of an interrupt is an IRQ will be received via the exception vector. This will be then dispatched to a handler if there is one, or a task will be set to be woken up. And at that point, it will then call the rescheduling function call, and then the interrupt will end. And having looked at this interrupt IRQ table, there are over 260 IRQ handlers, which is pretty sobering because this is indicating just how much hardware is really connected to the Shannon baseband and how hard it would be to fully emulate. But offline, if you want to take a look at that link to see all the different names, it's worth doing.
And another important component, especially talking about scheduling, are timers. They're a monumental component because without them, if a task goes to sleep, the baseband firmware in emulation just hangs. So what the baseband firmware expects is that the task will program a timer, which on expiry raises an IRQ, and then the scheduler gets invoked and kicks off scheduling of or rescheduling of the task. And without this logic, we will not get the emulation any further. So we need to implement them. We just had a very basic like mock-up implementation from the PAL init 1, but nothing granular, like fine-grained enough to make the behavior and make the baseband happy. The bad news here, those timers do not follow the specification of the ARM manual for the R7-R8 documentation, so we needed to sit down and reverse engineer them. It took us a couple of days. We prototyped them in Panda, in Python, and then once we were sure enough that our prototype implementation matches more or less what the baseband firmware is expecting, we provided the implementation directly in Panda in C, because as the timers are frequently fired and frequently need to fire interrupts, we could not have it running in Python code. We needed to have the directly integration inside the emulator. Here to the right, we see a snippet of how such a write to the timer would look like, and our comments to figure out what's going on. And you see there are a lot of different bits which needs to be handled and then need to be looked up. But yeah, with all of that, we got pretty far in the emulation and could do different things. And one of the more interesting things we did at the end of the day is we developed a mod kit.
So the mod kit allowed us to do something very important, which was modify the baseband to do extra things. And the thing we decided, the approach we decided to go with was to inject a custom task or more than one custom task inside the emulated baseband. These modules would be automatically paged in to a appropriate memory region within the emulator. And this allowed us to interact within and outside of the baseband in a more performant way. Our modules and our mod kit took care to kind of make it a nice environment to do modules in. So we abstracted away from even what the baseband's specific like memory addresses are, using this dynamic symbol resolution. We would resolve symbols not from a static analysis tool like Ghidra, but we would actually hard code these patterns in to be recognized on different modem images, and then have them be linked in to the C shared object when it's being loaded in. So kind of like a really cheap dynamic linker. And and with this mod kit, we developed our first task called the AFL task. And using this as dynamic simple resolution, it could kind of target different functions within the baseband fairly portably. And this task is, the flow of the task is shown below. Effectively, what it would do is initialize the setup for fuzzing. It would start a fork server, which is what AFL uses, and AFL will fork off different processes to be sent different data to. It will get work, so get the packet or whatever it is we're trying to fuzz. It will start work means it'll start recording coverage, and then it will send this data packet to a targeted task. And we can target any task based off different harnesses we use using our mod kit with this base AFL task. So fuzzing with AFL, we had a couple of campaigns. They were all centered around GSM and specifically into the session management, mobility management, and call control tasks. And the reason we decided to use GSM is because it's the easily accessible attack surface, meaning you can set up a fake base station and actually mount real attacks for very cheap, and there's no kind of crypto getting in your way because of the lack of mutual authentication. Our harnesses for each of these were less than 50 lines of C, which is very small and allowed us to quickly target different parts of the baseband with ease. And with our kind of like corpus we were generating from our fuzzing, if we realized we weren't kind of reaching the code, we could actually collect coverage, which is built in the Panda. And then we wrote an exporter to be able to put this into Drag and Dance, which is a plugin for Grija that is able to plot coverage, which you see here on the right. And after all of our fuzzing, we were not only able to replicate a couple of end days to kind of set up a baseline and ground truth for our work, we actually found a 0 day in the GSM's call control task. We reported this to Samsung, and they awarded us with a critical vulnerability and an SVE. So we actually were able to replicate this over the air as well.
But for now, we are almost out of time, so let's wrap this talk up. And just a short summary at the end. We probably convinced you that baseband firmware is huge and complicated, but nonetheless, reversing is possible, and we can uncover the secrets and basically the functioning, the inner workings of the baseband with reverse engineering. So that's awesome. Emulation itself was very tedious to set up and almost frustrating at times, but it was also very rewarding once it was working, because we could really detailed look into what things were happening in the baseband and how was state changing over time. And furthermore, as shown in the last part of the talk, we could even use it for do additional security testing, which uncovered real bugs on the real firmware, which will trigger on the real device. So that's pretty good. And the last thing we want to give you on the way is, please choose your tooling wisely. I mean, this applies to every project, but just to recap what we used: Ghidra to have a collaborative reverse engineering environment. We used Panda to have full system emulation capabilities. So something really important: if you deal with a full system you want to emulate, go for a full system emulator, not just a CPU emulator. And lastly, we used Avatar 2 for having capabilities of peripheral modeling and orchestration of the emulator itself.
And with that, we have some things we would like to release. So first is the Ghidra tools and the scripts that we wrote to help us kind of navigate through the baseband. This includes an auto renamer, debug annotator, and the firmware loader. We also have some reversing details, not all of them, but maybe more to come, and a log parser as well. And we also were releasing the code skeleton that we extracted from the debug symbols to help give you an appreciation for the scale of basebands, along with a set of Shannon firmware. And we're still working on it, but at a later point, we'll be releasing the emulator itself, Shannon EE. But for now, you can watch it on GitHub. And I'd definitely like to thank all the sponsors who helped make this work possible: SRC, NSF, NWO, the Air Force, and the Navy. They all provided funding across different funding vehicles, and they made this work possible. But that's all we have the time for. I really appreciate you staying to the end, and thanks so much, and we'll be happy to take any questions.
Thank you so much, Marius and Grant. Amazing presentation. Before we jump into questions, I have one question. How many Samsung devices did you break in your research?
So we didn't break, or at least I'm not aware of any device which we break, because we started really with getting the firmware and emulating it before we actually started trying around replicating things we confirmed in our emulator first.
Mm. And that's a key point of this. That's the reason why we actually decided to do this work in the first place, is because the existing research for doing baseband security analysis was all on device, over the air, and it was not only slow, but you have a large potential of causing your baseband and possibly even your phone to become corrupted if you're not careful. So we wanted a nice clean environment. We could take snapshots and roll back things before we ever start doing this kind of work on actual devices. So no, there's nothing in our phone graveyard yet, but maybe that'll change.
And did Samsung ever reach out to you after your research or on this research?
Well, yeah, we reported the vulnerability to them, and we've been working with them to report anything else.
Great, nice. Okay, let's go to the questions. There was a comment, even the 3310 had a baseband processor. Let me go through the comments. Okay, why is it direct debugging not an option for research? I'm assuming Samsung has a way to doing this.
Yeah, Samsung and every baseband manufacturer has a way to do this. Chip is at home, but the moment the chip is shipped on production devices, they will blow fuses to prevent that. So JTAG and all these things they should be removed and blown, so that even if you want to do a debug triage like an OEM wanted to do debug, they might not be able to do it. It might have to just kind of throw it out.
Okay. I'm not sure if it's a comment or a question by Ken that says magic constant XEF, XBE, XAD, XD, that's dead beef.
Yeah, exactly. That's what they used as a static canary for guarding the different stacks of their tasks. So it's a choice by the developers. We don't have anything to do with it.
All right. And to the previous question about the debugging for the researchers, I believe glitching is another follow-up question to it. Glitching against the fuse.
So that's probably possible. I'm not really, I would say, too much on that level of hardware security. Also, I would suspect phones today these are application processors that are meant to be secure, not only from the baseband perspective, but the fuse box in them is usually in a very secure element, a secure portion of the phone. So I'm not saying it's not possible. I just say you'd be going up against thousands of other fuses that are equally important. And I feel like the manufacturers would prevent this kind of thing. But
yeah, and
it's worth.
Yeah, just to stress it again, the baseband processor, the CP, lives on the same SoC as the application processor. So it's really just one big chip you would need to glitch against.
Right. It benefits from all the security enhancements to the application processor and trust zone, of which there are many and many years of work. So, but the approach I've seen in the community is actually to just, there's a recent paper that would, they actually attack trust zone and then were able within trust zone to pivot to the modem processor, meaning they disabled signing from the modem processor, at which point they could, I think, customize the modem and then implement a debugger, like a soft debugger, not like a hardware-based debugger. Not as good fidelity, but probably better than nothing.
Yeah. And lastly, glitching may be an option, but having an emulator at hand also could help to actually determine which points would be interesting to glitch, like when would interesting checks be skipped.
Very true. Yeah, with I assume the fuse control will be in trust zone, so those are also available firmware. Probably harder to analyze in some ways, but there are probably if statements that are vulnerable. So.
All right. Do you also want to check your own Zoom chat to see if there are any private messages?
Sure.
I don't have any. If I did, I may have lost them when my connection dropped. So.
All right.
So okay, so yeah, I got a private question to explain a bit more the concept of the cycling bit pattern that we used. I can just recap it once again very fast. So the base idea is that you have the peripherals, which are interfaced via memory mapped I/O, so via memory cells, and the firmware will basically spin in a loop waiting for a certain peripheral to be ready. And it checks if the thing is ready by just accessing a specific memory location. And this memory location will be set by the peripheral. Like 1 bit of this location will be set to 1, and then the firmware knows, oh, okay, cool, it's initialized, I can continue whatever else I need to do. So the cycling bit pattern is just exactly doing this. Whenever the baseband will access this location, it will return a different bit to be set to 1. So it's kind of just a very simple heuristic to get past initialization code. It's, of course, is not faithfully emulation of the peripheral itself, but this we did ad hoc whenever needed. Another question
also,
is,
no,
sorry,
go ahead.
no,
go ahead.
Okay.
Oh, I guess if there are 2 bits that needed to be set, then they would fail.
We have our cycling bit pattern handler is implemented good enough to handle multiple bits. We can set how many bits are set.
Okay.
And it will iteratively try all of them. So it gets to if you will have all set, it gets to brute forcing in the end, right? Okay. Another question was if we can put the links of the last slide in the chat. And yeah, absolutely. I will do this right ahead. But yeah, that's for it on the private questions I received. If you have any other questions, feel free to ask them.
Friends, this is the last talk for the day. Instead of having the breakout room, we'll just take in questions over here. So feel free to send in your questions over the Zoom chat. I know a lot of people have been facing issues for the breakout room because Zoom just updated their version of application and it's not backward compatible. That's a shame, but yeah. Any questions? Grant and Marius are still here with us, and they're happy to answer you. Also, the comment for the links for the last slide have been posted by Marius. We will be also posting it on Discord for people to use as well.
So we recently spoke at Black Hat with a similar talk, although this talk was more focused on reverse engineering. So when the video is released for Black Hat and you happen to be more interested into the exploitation side of things, I recommend you check that out because the slides are pretty much mostly all different. So if you have questions on that, but we're also here. You can ask us anything, AMA. So yeah.
There is one. Any recommendations, resources for learning Avatar 2 other than GitHub page?
So, I mean, something I somewhat hit during the talk is that I'm the main developer and maintainer of the Avatar 2 framework. So, I mean, I have an unfair advantage in when it comes to how to use it. But there is, on the GitHub page, I try to create some sort of documentation. On the GitHub page is a subfolder called Handbook, which basically gives you a quick start of the most important interfaces in multiple levels. And then there was an academic paper, which I can also link in the chat, which at least in academic talk describes the main concepts and some of case studies with the framework.
When I was learning it, I found that the source code was helpful once I started getting into a lot of the internals as well.
Okay. Any more questions? 30 seconds to go.
Well, if there's no question, we can also show a demo if you want to see it. I mean, we have way more things prepared than what we were able to talk about.
Probably over 2 hours worth of stuff condensed.
Maybe we reach out to you to do a workshop again.
Honestly, yeah. Okay. I mean, it would be kind of cool.
Right.
Yeah.
All right. Then thank you once again.